Well, good afternoon, good morning, or good evening, depending upon where you are in the world, and welcome to today's DevOps.com webinar. I'm Charlene O'Hanlon, Managing Editor at Media Ops and moderator for today's event, and I welcome you. As always, we have a great webinar on tap, and I am especially excited about this one. But before we get started, we do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you miss any or all of the event, you will have the opportunity to access it later on. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. And we are taking questions from the audience. So if at any time during today's presentation you have a question for either of our speakers, please don't wait, don't hesitate, just use your GoToWebinar control panel and submit your questions, and we will try to get to as many as we can near the end of today's webinar. Also, during today's webinar, we are going to have 2 polling questions, so hopefully we can get everybody engaged. And at the end of today's webinar, we are going to be doing a drawing for 4 $25 Amazon gift cards, so please stick around. Hopefully you'll be one of our 4 lucky winners. All right, with that, let's kick off today's webinar, which is Monitoring Kubernetes Health, How to Tackle Observability Challenges and Learnings from Major League Baseball. Our speakers today are Leo Schlossnagel, who is the founder and CTO at Serconis, and Riley Burton, who is the Principal Site Reliability Engineer at Major League Baseball. Gentlemen, thank you so much for joining me today. Very excited about this conversation we're going to have, and I really appreciate you being here.
Good to be here.
Thanks for having me.
Excellent. Well, so just to kind of level set today's conversation, we're going to be talking about Kubernetes monitoring, how it's different, some of the organizational changes and processes that are necessary to ensure efficiency and success. Going to learn a whole lot about how Major League Baseball did it, and Riley's going to kind of walk us through their process and everything that they learned from having to do it. So without further ado, I want to first actually ask the 2 of you to kind of introduce yourselves, tell us a little bit about what you do, who you are, tell us a little bit about your organization, and then we'll dive right into the conversation. So Riley, why don't you kick us off, please?
Okay, great. Hi all, I'm Riley Burton, Principal SRE at Major League Baseball. I've been here, I don't know, a year and a half, maybe going on 2 years soon. My background is a lot of distributed systems, and actually started as a sort of more of a hardcore engineer before moving into an SRE role here. I've been in the monitoring space for a long time. So that's me.
All right. Theo, tell us a little about yourself.
So I'm Theo Schlossnagel, avid computer scientist and industry participant in general, founder of Serconis. My background is in large-scale distributed systems design, and I helped design and operate some of the largest websites in the world over the last 20 years.
All right, great. Thanks so much to you both. Riley, I want to kind of just dive right on into the conversation. You said that you are an SRE engineer at Major League Baseball. So tell us why you guys decided to deploy Kubernetes.
Good question. When we figure out the answer to that, I will let you know. No, seriously. Major League Baseball is more of a tech company than people realize, I think. Yes, we do have a sport that we put on the field, but in order to deliver that sport and in order to deliver the sort of the amount of data that surrounds that sport, we have quite a big IT footprint. It spans all 30 Major League ballparks. It spans several on-prem data centers. It spans multiple clouds. This is everything from video processing to sort of on-field data processing to gaming, to everything you can imagine that is involved in the media that is baseball. So there's a couple of challenges in running a system that covers that much surface area. And one of the biggest challenges is how do we get a consistent artifact for deployment? Prior to the Kubernetes world, there were lots of sort of custom builds that were either sort of Maven based. Most of the shop here is Java, but then as other languages branched out, we started to have sort of a big sprawl in CI/CD. So solving that problem, plus how do you merge multi-cloud plus on-prem without using some kind of consistent API? And that's sort of where we settled at on Kubernetes. I think that the long-term picture for Kubernetes is not necessarily the way it's implemented now, but I think that the APIs will survive and maybe implemented under the hood in different ways, depending on the cloud, depending on the on-prem, depending on other ways. And I think one of the biggest points of this is we wanted to be agnostic, sometimes agnostic about where services are running, right? And have the capability to say, this ballpark is down, but there's certain services it has to provide, so let's yank those out and run them in GKE for the time being until we can fix the problem in the ballpark, and then we can shift them back over. So that kind of flexibility where we can move artifacts around at will is sort of a big driver for running Kubernetes in general.
Excellent. So what does your deployment look like? I mean, how many clusters are you running?
Quite a few. So we have several teams. So we sort of split our deployments across teams or products. Sometimes there's just a product that has a deployment or its own cluster. Sometimes there is a team that has multiple products running in a cluster. But in general, we have about 70-ish Kubernetes clusters running now. That includes 30 ballparks. So we have a cluster running in each ballpark on-prem using Anthos. And then we have, the other 40 are split among production deployment clusters, non-prod production deployment clusters, some sandbox clusters for the teams to experiment in, and then eventually deploy into production. Most of those are running today in GKE. We do have some remnant stuff still running in EKS and Amazon. So quite a few.
Yeah, sounds like. So who's involved actually in managing Kubernetes? I mean, do you guys have a mix of like managers and leaders, or do you have a dedicated staff, or how does that fall out?
So the systems team at Major League Baseball is pretty small. There's like 8 to 10 of us who are sort of the central core team who develops sort of CI/CD pipeline stuff. Monitoring is responsible for providing monitoring tools, I should say, not necessarily responding to events, although we do respond to our own. Mm-hmm. And then we largely push off the responsibility of the management of the cluster to the team who owns it. This is good and bad. It's good for knowledge sharing. It's bad because Kubernetes is complex, and inevitably the questions come back to the core team about, well, I don't understand why this is broken. Why is this broken? How to help me? That happens quite a bit. So we try to solve this problem of this cluster sprawl by reducing the number of tools we have at play. Various teams have gone off and either implemented their own CI/CD or grabbed a Jenkins tool, and we've sort of decided to write our own tool and go off in our own direction using Argo CD and related tools. So we try to democratize it as much as we can.
Great. So Theo, I want to bring you into the conversation now and talk a little bit about kind of monitoring Kubernetes and really what are some of the, the challenges that are associated with observability. Because I know monitoring Kubernetes is different from traditional monitoring. So, can you kind of walk us through why Kubernetes has kind of that unique observability challenge, those challenges that are just, like I said, unique to Kubernetes?
Sure. I think Riley started to allude to those fairly well. I mean, I think that there's this like layered reality of what it means to run software in production for consumers, right? At the end of the day, there's all these memes about how the cloud is just an on-premise data center run by someone else. That is not entirely true, but there is a lot of truth to that. So at the end of the day, your code is running on a piece of hardware somewhere, delivering something over a wire or a fiber or something like that. And those things don't always work, right? I mean, that's the history of computing, is that stuff doesn't always work. And the best dream of any computing engineer or operator is that when it doesn't work, it really doesn't work. It just stops working. But a lot of times they sort of don't work, right? So you end up machines don't go away, they become uncooperative, they start losing packets, they have different performance characteristics of other machines. And a lot of the legacy of monitoring and providing deep insight into people running systems is providing them the visibility to break that abstraction. So they're running this piece of software that should work a certain way, but it's not working that way. So what is the machine that it's running on doing? Well, Kubernetes sort of changes that paradigm because the abstraction that they provide is that you no longer need to care what machine that's running on, right? It provides a kind of a comprehensive fabric for deploying complex apps where it does the scheduling, it does the management, and all of this stuff is just taken care of for you. And that's awesome when it works. And when it doesn't work, the legacy tools really are, that abstraction layer becomes impenetrable, right? So that the real challenge that I see with Kubernetes, there's a couple of them, but one of them is that the abstractions that they've chose to put in place to give all of the benefits that Riley enumerated of why they've adopted it, also provide incredibly significant obstacles to understanding how and when things go wrong. So as he said, engineers, they're responsible for managing their own clusters, but that means that they need to have insight on how to fix it or what is wrong. The second part of that contributes to why that's so hard is that Kubernetes is really complex. And not only is it complex, it's very green, right? It is a very new technology. It's changing, right? So not only do you have to know this complexity, you have to adapt that 1 quarter from now when you do an upgrade, that complexity changes in its form and function, right? So it's hard enough to have, there's a skills gap in the market today for people operating Kubernetes. It's very difficult to keep up. So on top of figuring out how it works and trying to make it work, also having that cognitive load of trying to figure out how to make monitoring work for you in that ever-changing ecosystem is a huge challenge as well.
So how do you address these monitoring challenges then? I mean, it seems like some of the problems would be too difficult to overcome with just any sort of observability solution. So how do you guys do it? How do you do it?
I mean, I think that there's some truth to that, right? There is no silver bullet for this. You don't have a magical solution, but sadly, as everyone fixes one broken abstraction by layering another abstraction on top of it, that is sort of the answer to that. So what our aim here is to take that ever shifting and changing landscape with evolving APIs and evolving components, and in our case, what we're really considering as like the critical problem is that there are evolving pathologies of failure. So as things change, the way that they can fail changes inherently, and then they have cascading effects. Our goal is to encapsulate those into a surface that doesn't appear to change that often, right? Give a consistent, reliable, repeatable, coherent view. And we take the burden of all of that shifting landscape under the hood and expose something that doesn't increase the cognitive load on engineers trying to operate it. So the last thing you want to know is, well, the first thing you want to know is something's wrong. But the last thing you want to do is show up at the tool and realize that it's telling you something you no longer understand, because the last time you looked at the tool, it was reporting different types and different generic failures. So a lot of our work is, I mean, at the end of the day, it's productizing it, right? That's what it is. It's really turning that into a product that people want to consume, in this case, operators.
All right, great. So I think now actually would be a good time to push out one of our 2 polling questions. So if you guys will bear with me here, I'm going to go ahead and launch the first poll. So hopefully we can get the audience as engaged as possible. The question is, how challenging is gaining visibility into and managing the costs of your Kubernetes clusters? Go ahead and make your selection here. And the choices are valid: very challenging, challenging, somewhat challenging, not challenging at all, or I am sure, or unable to say. You can go ahead and make your selections. And while we're waiting for everybody to do that, I just want to remind the audience that we will have a question and answer period after today's discussion. So if you have a question for either Riley or Theo, please go ahead and use your GoToWebinar control panel and submit your question, and we'll try to get to as many as we can. All right, I'm going to go ahead and close out the first polling question, and then while we're at it, we're just going to go ahead and push out the second polling question. The first one has been closed. The second one is being launched right now. The question is, to what degree have you experienced higher than expected costs to run your Kubernetes clusters? You can select from our Kubernetes costs are much more than we expected. Our Kubernetes costs are a bit more than we expected. Our Kubernetes costs are about what we expected. Our Kubernetes costs are less than we expected, or I am unsure or unable to say. Go ahead and make your selection. We'll give you guys about, I don't know, 30 seconds more to go ahead and make your selections, and then we'll go ahead and get back to our conversations. Also, a quick reminder to the audience that today's event is being recorded. So if you miss any or all of it, you will have the opportunity to access it later on demand. So hopefully that'll help some of you. In case you have to leave the webinar and come back, you'll be able to hear the whole thing. All right, with that, I'm going to go ahead and close out the poll, and then we're just going to dive right back into the conversation. So Riley. So
Yes.
I know that sometimes maintaining cluster health can be a challenge. So, and I'm sure you guys have had your share of challenges. So what do you experience, and how do you use the health insights that you derive from it?
So most of our clusters, I wouldn't say most of them, but in our overall environment of the 70 plus clusters, something or some portion of those clusters are in various states of broken continuously. This means people are deploying stuff into a non-prod cluster, for example, and not sort of paying attention, and it goes into crash loops because they have some bug that they're not really ready to deploy into production, or it's crash looping due to permissions that haven't been effectively set for their pod or whatever they're running, right? Since there are so many clusters, there's no way for a centralized team to manage all of that and understand the context of those deployments across all of that. So what we tend to do is surface this information, direct those. You can see we use all of these, but if you're looking at the slide here, direct these alerts to the team that owns it, and we use Terraform for that behind the scenes to set up some rules that allow the alerting to go directly to the team that owns that cluster, including ourselves for the clusters that we own. And then when the team can't manage that, so we surface the information, and if they genuinely get stuck, they come back to us and say, I don't know what it means that I have disk pressure, right? Or I don't know, what does it mean? Like I ran out of inodes. I don't know what that means. And that does happen all the time. So going back to a prior point, we try to democratize as much as possible. We do see crash loops quite often. We do see pods that are stuck pending. People deploy something, they don't realize that it actually never deployed. It just sort of sat there trying to deploy for a long time. After an hour, we say, hey, you tried to deploy this and it didn't deploy for an hour. You probably want to take a look at your deployment, and that it sort of prompts them to go figure out what's wrong. That's how we deal with it today. My guess is that will evolve going forward as we get better and better at this.
So I guess the next obvious question then is, so what have you learned, when you guys have this whole Kubernetes management, monitoring, deployment, what have you learned about monitoring Kubernetes specifically?
A lot of stuff. How much time do we have? All right. We'll start at the top. So number one important lesson for Kubernetes is metrics consolidation. Earlier deployments of Kubernetes took the approach that we would install Prometheus on each cluster. We would have this sort of siloed monitoring tool running in the cluster itself, which is probably works fine when you have a finite number of clusters and it's something you can manage. But when you have the footprint that we have, it's basically impossible to run like that because you don't know where things are coming from. You have to configure alert management for Prometheus across 70 clusters. It's a lot to actually deal with, and they become in various states of non-compliant for various alerting stuff, right? So the need to take all that data that's coming out of all of these clusters and put it in one spot so we can have one set of alerting that manages the 10 to 15 major issues that can happen and allow the teams to then go further and sort of layer on more complex rule sets if they want to about their own particular, or modify the rule sets we provide by default, so that they can get more actionable information out of their cluster. The other thing is there's so much noise. This is all part of consolidation. I think Curtis asked a question here that's related to this. He asked, do you ever use the control plane metrics to debug? It seems like a large amount of static or white noise except the output from the scheduler. That's a great point. If you look at any Kubernetes cluster and say, how many time series are actually available? In our 30 to 40 node clusters, we see about 750,000 time series coming out of that cluster every minute, if we were to just take the whole fire hose, which is just impossible to reason about. It's so much data, it's almost useless. So what we do is we filter out 90% of it and don't even, just drop it on the floor. And we keep that remaining set of time series, about 15 to 30,000 time series per cluster, per larger cluster. That lets us get at those 15 to 20 actionable things, right? So we boil down the space of possible crap, excuse my French, to a set that we can actually do something about. Like this pod is crash looping, we can do something about that. You know, this node hit memory pressure and started evicting pods, right? We can do something about that. So we've sort of cut that set down to a reasonable set to manage. Second thing we have learned is that the push model of Prometheus doesn't work. I'm sorry, the pull model, I got confused by myself. The pull model of Prometheus doesn't work for us. And that is because we have a complex network which spans ballparks all over the country. Sometimes it spans VPNs, it spans 2 different clouds, it spans on-prem, it spans all kinds of stuff. And it's inevitable that we have drops. And when we were using a pull model with Prometheus for a lot of this to try to centralize the data before we started using the Serconis tool. And we would see holes in the data. We would have a 5-minute dropout somewhere, the polls would fail. The only way to solve that is to figure out some kind of backfill process, which is actually really hard to manage. So we've sort of jettisoned all that and gone with a push model for receiving the data and centralized processing of that data. And then I think the biggest one is turnkey, right? There's so much to manage. And I think this is what the teams at MLB appreciate about the solution we have today, is they can just launch stuff and they don't have to think about, am I going to get an email or a PagerDuty if this thing is crashing? They don't have to think about that anymore. They know when they launch their cluster, we install our cluster services. That means that cluster is managed. That slide that was up before that has 15 to 20 set of sort of important alerts, they will get those. And they don't have to think anymore about, oh man, I got to go set up my alert manager for configuring my alerting on my Prometheus on my cluster and manage it all themselves. That all goes away. And they just get told, hey, this is broken, go look at it. And then they get, of course, some nice dashboards to look at the history of it, right? So wherever turnkey can be used, wherever we can apply the 80% use case to a cluster and then let the team go off in their 20% space and make their own special configurations for their own special use case, that works, I think, extremely well in our environment.
Excellent.
Oh,
Excellent.
I have one more learning.
Go.
Okay. Really, so I'm glad you guys asked the poll question about spend, because this is sort of a hot topic here at Major League Baseball today, and that is understanding resource utilization is sort of a hard problem without a centralized look at your metrics. That is, I have these pods that are requesting 8 CPUs and they're using a quarter of 1 CPU. Why am I spending? Because you're spending money on the node when you're running in the cloud. Like you have this worker node and you're using some small fraction of the resources on that worker node. And further, there's a matrix there of what sort of CPU and RAM am I requesting versus what am I using. And then on top of that, there is how many pods are running in my environment and how many pods are allowed to run per worker node. Some of that is limited by network, some of that is limited by arbitrary choices about performance, about what pods are running there. It's not sort of simple to get that part correct. However, it is important to be able to surface that information and make decisions about spend based on what you're actually using. So it's good to see that, you know, there's a good portion of people who are saying they're spending a little bit more than they thought. And we run into this too, as a large organization. We have situations where we have some team has launched a GKE cluster, right? And they've launched it in non-prod, and that's great. However, because it's GKE, they launched it into US Central 1, right? And GKE says, oh, I need a worker node in each of those zones, so it launches 3, right? But it's a non-prod environment, and they have to run, like, say, 10 pods on it, and that all fits on one node. So they have all this, 60% overhead in their cost because of the nature of how Kubernetes works. They don't need all that capacity, but just because we have so many clusters and just because of how it's split up, we end up with this overhead in cost. Now it's easier for teams or for organizations who have sort of a smaller cluster count and can pack more tightly. But even there, I would argue there's a lot of probably waste running in your clusters that you're not even aware of, that you should probably take a close look at. And those are my major learnings.
Ephemeral nature? Is that due to the ephemeral nature of containers?
It's due to that. It's due to a sort of understanding how you are doing horizontal pod autoscaling. Are you doing it like most people do it, using like the CPU metric on the, CPU is there to be used. And a lot of people will scale because my CPU got high. But the CPU getting high doesn't necessarily mean that your latency has gone up. It just means you're using the cores that you said you would use. We struggle with this too. We actually have several of our autoscalers are set to scale based on that. But we're getting smarter about this and doing autoscaling based on the metrics we derive from our actual utilization here, right? So we can pull the utilization, we can run some math over it and determine, oh, we actually don't need to scale because our requests per second are N, and we know that historically we've been fine with this level of scaling at that request rate. So there's no reason to scale right now. And that saves a lot of money over time.
I would second that. I mean, for 20 years, it was my primary objective to build efficient systems and do capacity planning. And even after all of that, I would say that I am both pretty good at it and horribly wrong. Almost every time I try to go in and predict the resource requirements of a complex system. And Kubernetes, given that the control is so much more granular, overestimation is incredibly common. You go in and you say, these are the resources I need, and the system works, and you were like, I'm right. But if you actually look into the hood, you're not nearly using the resources that you thought you were, and there's a huge opportunity for cost savings.
Yep.
Awesome. So yeah, I want to go back, CO, to some of the monitoring challenges. We talked about it earlier, but yeah, I think some people, I guess if we can kind of wrap a story around or an anecdote around some of those unique challenges that some organizations are dealing with, especially organizations that really aren't using Kubernetes and containers at the moment, but are possibly thinking about it. Can you kind of expand on some of those challenges, maybe that some of the specific problems that some folks are experiencing out there right now?
I think Riley touched on those a bit for Kubernetes. I mean, I think that there's this, I mean, all operators know this, but there's from the outside, a little bit outside the IT realm, and sometimes even in the software engineering realm, there's kind of this mythology that when things break, you just fix them, right? And it's never quite that simple, right? So when systems break, each system that you have breaks in unique ways. And as that system launches new versions of the software, like, say you're running a Postgres database, well, the way Postgres 9 would break is different from 10 and 11 and 12. And they stay more or less stable now in the later versions. But each system that you ever deploy, they have unique pathologies of failure. And then as we build these large-scale distributed systems, you have lots of interplaying parts that all have unique pathologies of failure. And as an operator, when they break, it's your job to take the kind of the cause of the failure and remediate that as quickly as possible. So the real challenge in all of this monitoring is developing appropriate domain knowledge to be able to get a really decent list of those unique failure pathologies so that you have a runbook, right? So if I'm running Kubernetes, what could go wrong and what do I do about it? And that's honestly really difficult, right? The skills gap in the market today for people who understand Kubernetes taking that to like a discrete set of pathological failures and prescriptive responses to those is almost non-existent. And I won't claim we're 100% right, but I would say that we take a really good, honest tilt at that windmill, and we've produced some pretty good results. I think MLB is using it to great effect. But the idea, like on the slide, you can see, I mean, crash groups, job failures, CPU utilization, all of these things are kind of recurrent, specific failures that we see in Kubernetes deployment across a wide range of customers. So our goal in that is to make these turnkey so that you don't have to worry about figuring out which one of these you need to monitor and making sure it's working right. And we also have, I mean, from the Serconis side of things, Kubernetes is just one of many things that we monitor. We try to do this for all of the various things that we monitor to distill down, like, so you're monitoring Postgres, or you're monitoring a web service, or you're monitoring API service. Like if you're monitoring an API service, which MLB also does, you really need to understand the performance pathologies there, right? It's pretty easy to tell when something doesn't work, but it's a lot harder to tell when something has behavioral decay, right? Where you're just sort of disappointing all your customers as opposed to denying them service, right? So being able to really dig into that is a deep, complex statistical problem. And our goal again there is to make sure people are aware of what the problem is and make sure that they don't have to learn, you know, deep, complex statistics to be able to track it and deal with it.
Excellent. Excellent. So, you know, I know that, you know, a lot of organizations have been reticent to adopt containers and especially Kubernetes technologies because it's just so complex. And, you know, do you see this, the monitoring of Kubernetes kind of part of that complexity, and your solution actually kind of eliminates some of that complexity to kind of maybe ease the use in general?
There are many facets of complexity in Kubernetes. Monitoring is absolutely one of those, and anything that we can do to reduce that complexity makes adopting the whole thing more palatable for customers. You can't just put in Serconis and remove one complexity and think it's not too complex. Mm-hmm. There's still other complexities in there, and there are other great tools to solve those things. But the benefits that Riley outlined are really compelling, right? Like you get determinate, it's a lot easier to achieve like deterministic asset deployment, artifact deployment, right? You know what's running there, right? You don't have a lot of the complexities of managing failure because of the way things fail in Kubernetes and are designed to be rescheduled and restarted and deployed and shifted over are very prescriptive. So it's not bespoke and creative anymore. You fit yourself into that model, and then suddenly you really can reap the benefits of that model. So I will say that Kubernetes is ridiculously complex. It is still very hard to run. Everyone is trying to improve that. We're doing our part on the monitoring side, but the reward, the value that you can extract by adopting it is very material. So it's definitely worth considering for everybody, and every quarter that passes, the decision to not do it will become harder to make.
So Riley, on your journey then, you know, the decision to adopt Kubernetes, was that an easy one for Major League Baseball, or did you guys do a lot of hand wringing and hair pulling?
I think we still do hand wringing and hair pulling about it. We still have sort of stuff running in Kubernetes where we're like, does this make any sense to run here? Should this be just a set of VMs somewhere? There's the classic answer for that is anything that needs a persistent volume, which is still to this day a very difficult thing to wrap your head around as an engineer. Is like, I have a disk, like what does that mean, and what happens to the disk in these certain weird edge cases? You know, that if you have data that you care about, it's hard to make the decision to run something that requires persistent disk inside Kubernetes today. It's not impossible, and we do it. We do it, but there are definitely challenges there, I think. So I don't know. I think it's the right decision for Major League Baseball. I think because our footprint is so vast, and because we need to find where we can to settle down the surface area of stuff we have to manage, like running our set of software, which is pretty expansive, on myriad different deployment mechanisms or VMs here and Kubernetes here and this other different thing somewhere else, that would be, you know, Cloud Run or whatever. That would be a very, very much more difficult thing for us to manage. You have bespoke monitoring for your VMs and your deployment there. You would have bespoke monitoring for your Cloud Run stuff. I'm not even sure how to do that. You have, you know, you have Puppet and Chef mixed in. It just becomes a mess. We have Ansible running still in certain places. So I think it simplifies the thoughts about how we run our infrastructure down to this set of things. We have to become experts at this particular set of things, which is still very complex. But if we can become experts at this particular set of things, then we can apply that knowledge to, you know, software we have to run on premise. We can apply that knowledge to, do you have a Docker file, and does your software build into a Docker file, like into a container? And if so, we can run it for you. We just have to figure out all the mechanisms to make that happen. It simplifies that portion of the software development lifecycle and gets us down to, we have a container, let's just run it in the proper place.
I love analogies for these things because they tend to resonate with people that think that they want to deploy everything under Kubernetes. I think of Kubernetes as some sort of piece of infrastructure like a school bus, and it might be fantastic, but that doesn't mean everyone should use a school bus to get everywhere they're going. And in the Kubernetes community, there's a lot of times there's an argument that says, look, Kubernetes is not a school bus, it's a road system. And if you look at it that way, which I will give you, if you can achieve that, that means you can never get a 2-day package delivery because you've foregone planes, right? There is always some piece of infrastructure or technology that can just truly benefit from a different way of thinking. So the idea that everything will be shoehorned into Kubernetes, I think, is not only like wishful thinking, it's also counterproductive. But it is fantastic, so people should consider it.
Yeah, it's
the 80%. It's certainly gaining traction.
Yeah, it's the 80% use case. The 80% use case fits into Kubernetes really well. We're running RESTful services for the vast majority of the stuff that we deploy. That fits really, really well into that model, right? And then we have a database like Scylla or Postgres or Cassandra or whatever. Doesn't fit so well into that mega, but we still have to run it. We still have to run Redis. You can run Redis in Kubernetes, but we don't. Or we have to run Memcache. We run that on VMs, right? So there are things in our world that don't fit that use case very well, and I think that will continue until sort of persistent storage gets a lot better, and until the pathologies of problems and how the scheduler resolves those problems are much more tunable.
Excellent, excellent. Well, I think we are going to be opening up the question and answer period here in a minute. We've gotten some great questions in so far, but please, if you have a question for either Riley or Theo, please go ahead and use the GoToWebinar control panel, and we'll start diving into those questions. Let's see, Riley, I know you already answered one question here. So, okay, here's one. Ryan, do you permit the cluster admin role to engineers?
We do. We, because, well, not to all of them, but to the ones that team owns, yes. They are allowed to do pretty much whatever they want. They are the owners of that cluster in that sense. If and when, I should probably say when, but for now, if and when we move to a smaller set of clusters that are more centrally managed, then that will probably change. But for now, it's true, yes.
Okay. All right, great. Let's see, here's another question for you, Riley, I think. What governance do you have in place to control dev engineers over allocation?
So today we do not pigeonhole them into what they can request. And some of this is the way budgeting works inside Major League Baseball, and the amount of money they're allowed to spend on their team sort of governed by that team. As an organization, of course, we care very much about how much money we spend on infrastructure. So what we try to do is provide them tools. One of these tools is Serconis and their resource utilization sort of graphs and charts around now how much are they requesting versus what are they using on the memory and the CPU side. We also have looked into tools such as Goldilocks or the Kubernetes resource allocation report that came out of Zalando, which does similar stuff. It says, you've requested 8 CPUs, you're using 1. What are you doing with all that space? What's missing from those tools is, and I hope we can answer this with the data coming out of Serconis, and I think that we can, is your pod limits on worker nodes, which comes up today. No matter how tight you can get in your request allocation and being right on the nose with what you need to use, it doesn't matter if you can only run a fixed number of pods on each worker node, because then you're going to launch another worker node anyway, and that's where the cost comes from. So we employ lots of tools, but today we do not pigeonhole them into any kind of resource allocation usage.
All right, great. Plenty of time for questions, guys. If you do have one, please go ahead and use your GoToWebinar control panel and submit it. Here's an interesting one. Can Serconis replace the monitoring and alerting that runs in GKE? What I mean is, can you drop the GKE monitoring once you have Serconis up and running?
Yes.
You can. The advantage of doing that, I mean, it doesn't hurt to have overlapping monitoring, but one of the significant advantages of using the Serconis Kubernetes monitoring is that it is not GKE specific. So if you are running Kubernetes outside of GKE, for example, in Amazon or on premises, then you get a consistent workflow and view, right? So you get the same thing everywhere, and engineers don't have to learn different things. So the short answer to that is yes.
Yes, the GKE stuff out of the box does work. I think we still have that in place in a few places at least. We don't tend to reference it ever. So it's there, we haven't turned it off. As we get into more cost savings measures, we'll realize we don't need to be doing this. If it's costing us money, turn it off. We haven't gotten there yet.
All right, great. All right, Riley, here's another question for you. You mentioned some of your clusters had 30 to 40 nodes. What problems have you run into as you tried to scale up clusters to large numbers of nodes? And is it better to operate larger numbers of smaller clusters?
So that's a great question, Tony. So a lot of the problems we've run into are what I would term shoot yourself in the foot during setup problems. There is no realistic limitation on the number of nodes. There is a limitation on the number of nodes you can run in a cluster, but there's no realistic limitation for most workloads. A lot of the limitations that we have are surrounding how we split up subnets. Actually, we have a subnet for the worker node itself, and then we have a subnet for the pods that run in the node. And that subnet is fixed size because we have so many teams and so many clusters. We actually run out of IP space if we scale too big, or if we put too many pods on a single node. We're in the process of fixing those subnet issues. So that was one of the major issues we run into as we scale up, is we run out of IPs. Because there's so many pods cycling over and over and over again that the IP space gets consumed and the IP doesn't get returned for several minutes and blah, blah, blah. So we ran into that issue. We never really ran into any issues outside of that, aside from thundering herd problems when we're scaling up. Initially, we were scaling on CPU, and we would have the cluster decide I have to spin up some more pods in this particular deployment because we're running out of CPU here, and it would say, okay, well, I don't have any space to put them, so I need to launch another worker node. It would launch a worker node, and then it would schedule the pods, and it would, for some reason, the load balancer would send them all of the traffic at once, and then they would crash and burn, and then we wouldn't actually be able to scale at all. We had problems like that. The Google load balancers do not do well at sort of slowly turning up the traffic. They just say here, which is an issue. We're still actively looking for a solution to that. Don't know what the answer is yet. It may be something like an Istio or some other load balancer that can be smarter. Those are the major issues that we've run into. I would say The problem with operating a large number of smaller clusters like we do today, because I don't consider 30 to 40 nodes very, very large. Most of the clusters we run are like 3 to 5 nodes. They're really small. The ballparks have 3. The various other development clusters are 3 to 5 nodes. Is that you have this cost overhead. Most of the workloads that are running there do not consume the resources that they've asked for, and it's much easier to pack them tightly and save money if you have a smaller number of large clusters. Right? If I have a 100-node cluster, I can pack everybody in there and I'm done with one cluster. There are reasons to split off workloads so that we don't, interfere with each other. But from a cost savings perspective, I would argue that a large number of smaller clusters is a bad idea. There's too much overhead in cost.
All right, great. And here's a good question for you, Theo. I think this one, it would be good for you. Can you elaborate more on PID pressure?
I think that so there's a certain limitation to basically it's a kernel resource limitation in Linux. Linux manages a tremendous number of resources, virtual memory, CPU, disk, I/O scheduling. It has to run processes and threads. And there are a limited number of processes that can run at any given time on a Linux kernel. And when you start packing things really tightly and cycling things, then you can actually build up so many processes quickly overturning that you end up starving the system of resources. So it basically ends up being a resource limitation issue.
We have never run into PID pressure. We have run into disk pressure and memory pressure. The way Kubernetes handles those is slightly different. PID pressure, it will evict processes. It'll start evicting pods based on some kind of decision about what's okay to evict. Memory pressure will do the same thing. Disk pressure, it actually will do the same thing. So in all these cases, we get these alerts. We get them mostly for informational purposes, because when that alert goes off that you've had disk pressure or memory pressure or PID pressure, what's actually happened is the scheduler has said, this worker node is full, so I'm actually going to launch another one and reduce the pressure on this. So what happens is we get the alert, you're like, oh no, memory pressure, but then it's already launched another node and moved work onto it, and then the memory pressure alert goes away. It's more informational for us, unless you have set a fixed size to your cluster and you said it can't get bigger than 40 nodes, and you're at 40 nodes and you start getting memory pressure and disk pressure and PID pressure alerts. That means bad, because nothing else can get scheduled, nothing else can run, because you don't let it scale up any bigger. Right? So those are really important things to monitor. Most of the time, hopefully they're informational.
All right, so doing a quick time check, we are about 13 minutes to the top of the hour. We still have plenty of time for questions, guys, so please go ahead and use your GoToWebinar control panel if you have a question. Here's another one, so slightly long, so bear with me here. Hi, I believe you slightly touched on running on the DBS on Kubernetes, the databases on Kubernetes. Are you currently running on any stateful sets such as Postgres, Mongo, Kafka, etc. in production on Kubernetes? This is one thing we are still debating, whether to put these on Kubernetes versus on traditional virtual machines. And what would you recommend, and any issues that you have noticed running these on Kubernetes?
Yes.
So, a lot there.
We do not run, so for Postgres in general, we use Cloud SQL. We don't have any Mongo installations. That's not true. We have a Mongo installation. It is on VMs. We have a Kafka installation. It is on VMs. We have a Scylla database, which is a Cassandra clone. We have that on VMs. We do have our own APM solution written in-house that does run with persistent volumes. The nature of this is that we have to jump through all kinds of hoops to make sure that the pods that need the data on the disks get scheduled on the machine that has the disk, because we use sort of local NVMe on the drive, on the machine itself. So yes, we're running it in Kubernetes, and yes, we're running a persistent volume, but that persistent volume is fixed, and the pod can only run on that node. So for purposes of, it's a VM. For purposes, it's a container, but it's always running on the same node. Because we can't relocate the disk. Now, we have prior iterations of this solution did use persistent volumes that could relocate, right? So GCP would unmount it, move it to the new worker node, remount it. There are issues with that. You have to understand how persistent volume remounting happens, what happens if the worker node goes down in terms of like your file descriptors on the what file descriptors are still open. We ran into corruption issues where that was being relocated when workloads were being moved for whatever reason. It became very hard to manage. And this is the problem, that stateful sets need to be really deployed as stateful sets if you expect the data to be consistent. If you don't care and it's more of a cache file system, then you can just run whatever you want. But for data that you care about, you have to be very, very careful about how the persistent volume claims are constructed. So my recommendation, if you're thinking about it, would be don't do it unless you have a very, very, very good understanding of how persistent volumes fail.
All right, great. All right, here's a great one for you, Riley. What is a takeaway from your experience that you would communicate to business stakeholders or peers at other companies?
It's a good question, Fred. I would say that invest in transferring knowledge about how Kubernetes operates to the teams that are going to be interacting with it. In other words, push the knowledge out to the development teams who are actually running on this, because unless you have a large amount of resources to hire a very large SRE team, it's not really possible to manage all of that sprawl with a small team. You need to get everybody involved, pushed out. In the alerts that we generate, which is on the screen here, a lot of them are on the screen here, we actually provide a little link in there to a page that says, I got a disk pressure alert. What does that mean? How do I deal with it, right? Which links off to lots of information about what does disk pressure mean inside Kubernetes, how you could possibly deal with it. You probably either ran out of disk space or inodes on that particular worker node. What does that mean? It probably means your logging is out of control and you wrote too many log files instead of spitting them out to the console. Like, it's a common mistake. So we try to provide the teams with that knowledge, and it lets them wrap their head around how it operates. And I would say to business stakeholders, understand the cost. We are bad at this and we're getting a lot better, but we have, I would say, 2x overhead in what we should be spending right now versus we were able to save buckets of money just last month because we concentrated on this resource allocation problem, and we've just scratched the surface. As we get better and better at this, we'll be able to reduce our infrastructure costs quite a bit.
Tilting and rephrasing your first comment, which I think is incredibly poignant, is that software engineers that have not built software to run on Kubernetes have a set of assumptions that will make it less reliable and more difficult to operate if they just apply that knowledge to Kubernetes without alteration. And by forcing the knowledge transfer on the nuances of how Kubernetes works and how it operates into those teams, they come to the playing field to kind of with their eyes open about how to build software that will be operable on Kubernetes. So don't have a silo there. Do not isolate the knowledge of how Kubernetes works and all of its nuances into a single team, because you will end up producing software that actually just burns money.
All right, we are about 6 minutes to the top of the hour. I think we have time for one more question before we close it down. So Riley, what is the typical stadium local storage size? And is the video content stored with the same storage pool?
That's a great question, Kathy. I think we have, I would say, somewhere near 2 to 5 terabytes of space in each stadium, if that's what you're asking me. It's like I think there are 4 to 8 actual physical machines running, vCenter and then Anthos on top of that. Video content stored with the same. So video content is actually immediately shipped off. Actually, video content that comes out of the parks is shipped via MPLS, over UDP, over AT&T and CenturyLink networks simultaneously, and then it's really complicated. And then we resolve best packet on the other end, in case some of those network links get a little fuzzy, we pick the better one, right? And then we resolve that to storage and transcoding and elementals on-prem, and then we drop that in a GCS bucket. That's how we do the video at a very high level. But there's a little bit of storage there for some local processing, because there are, in every baseball stadium now, there are 12 cameras that do ball tracking and player tracking. And from those 12 cameras, we derive where the ball is, how fast it's moving, how fast it's spinning, and then we also derive where all the players are, where all the, where all the people are on the field, including umpires, and where their body positions are in 12 points of presence. So wrists, elbows, shoulders, hips. And so we can do some really cool stuff with 3D rendering of actual game content in real time. You don't know that because it hasn't come out yet, but it's going to be really cool.
Sounds pretty cool, actually. So, all right, guys, we're 4 minutes to the top of the hour. So at this point, I'm going to close out the question and answer period. If we didn't get to your question, I apologize. We had so many great questions, though. I'm really I'm impressed by the quality of the questions that came through. So if we didn't get to your questions, please know that the folks at Circonis will be getting a copy of all the questions, and I'm sure they'll be more than happy to follow up with you to get your question answered by either their company or by Major League Baseball. Also, a quick reminder that today's event has been recorded. So if you missed any or all of the event, or if you just want to watch it again, you will have the opportunity to do so. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. And the webinar is also going to be living on the devops.com website. So you can always go look for it there. Just go to devops.com/webinars, look in the on-demand section, and it should be right there waiting for you. All right, I did mention at the top of the hour that we would be doing a drawing for 4 $25 Amazon gift cards. So without further ado, let's go ahead and do that. Our first winner today is Chad M. Congratulations, Chad. Our second winner today, yay, is Brian V. Congratulations, Brian. Our third winner today is Terrence L. Congratulations, Terrence. And our final $25 Amazon gift card winner today is Francesca L. Congratulations, Francesca. We'll be following up with all 4 of you offline via email to get your $25 Amazon gift card over to you. So please check your inbox, and if you don't see it there, please check your spam folder. Theo and Riley, thank you so much for your time. Great presentation, great conversation, love the information. And judging from the quality of the questions that came in, I know our audience got a lot out of it too. So thanks again, really appreciate it.
Thank you.
Thanks.
All right. Also want to thank the audience for joining me today. This is Charlene O'Hanlon, and I'm signing off. Have a great day, everybody, and please stay safe.